All right, we'll continue with section 1.5. Now we move on to the second part, which is logarithmic functions. All right, so we had an expression like, fx is equal to b to the x. Okay, this is called the exponential function with base b. What that means is that b of x is equal to y, right? Okay. The inverse function is going to switch and send y back to x. And so that is the log function, log b of x. Well, I shouldn't say that. Log b is the inverse function for that. All right, so let me just go ahead and write something here. 2 to the third power is 8. Okay, 2 to the 0th power is 1. 2 to the negative 1 is 1/2, right? So you can, these are exponential expressions. You can, for each expression of involving an exponent, you can write a equivalent logarithmic expression. So here you can say log base 2 of 8 is 3. And you say, what? Okay. It is, and I have to confess, it is kind of difficult if you're not familiar with this. Right? I mean, it's like you see the same numbers, 2, 3, and 8. But here, you're saying log base 2 of 8 is equal to 3. What does that mean? Here's what it means. This value of a logarithm is the exponent to which you raise the base 2 in order to get 8. So the question is 2 to what is 8? Okay, the answer to this question is the value of the logarithm. So the value of log is actually the exponent. Okay, again, the question is 2 raised to what number is going to give you 8? And the answer is 3. All right, log base 2 of 1 is equal to 0 because 2 to the 0th is equal to 1. Okay, log base 2 of 1/2 is, well, 2 to what power is 1/2? And the answer is negative 1. Okay, and you can play around with these things for a long time. When you have log x without any specific base, this is assumed to use base 10. And this is called the common logarithm because it's commonly used. By whom? By people like seismologists who have the Richter scale for the magnitudes of earthquakes, or light intensity used by people who study stars, and decibel measures for people who study acoustics, the sound loudness. All these are measured using the base 10 logarithms. Okay, so base 10 is a common log. And so you can say, what is, if I ask you, what is log of 1,000? Can you tell me what that is? This is log base 10, right? Log base 10 of 1,000. The answer is the exponent to which you raise 10 in order to get 1,000. Okay, so that the answer is 3, since 10 to the third is 1,000, right? What is log of base, log of 0.01? Okay, again, this is 10 to what number is going to give you 0.01, which is 1/100. And the answer is negative 2, right? Because 10 to the negative 2 is precisely that number, 0.01. All right, so for every exponential expression, there's a log expression, and every log expression can be rewritten or translated into an exponential expression. All right, now the reason, and I think you can tell that this is, the opposite, right? 10 to the third is 1,000. All right, so this is sending this function is sending 3 to 1,000. Right, this function is taking 3 to 1,000, and this function is sending 1,000 to 3, and so that's exactly the opposite. All right, so log base b of x and maybe I shouldn't call these same functions. G of x is b to the x are inverse functions. So keep that in mind. And because of that, the graphs are going to be symmetric with respect to the line y is equal to x. All right, so if I were to graph 2 to the x, it's going to look like this. Okay, so this is 1. This is 2 to the x. If I were to do the log base 2 of x, it's going to go through 0, 1, and it's going to be a very slowly growing function. And this will be log base 2 of x, and they're going to be symmetric with each other. Okay, both of them are increasing wherever it's defined. 2 to the x is defined for all reals, and it is an increasing function. The rate of increase gets faster and faster. Log base 2 of x is defined on its domain, which is the set of positive integers, and it is continuing to increase, even though the rate of increase becomes slower and slower. All right, so that's something that you should remember. All right, so I said log of x with the base 10, and that's called a common logarithm. And then we have another very natural choice for the base, which is it's a base e. That e is the number I introduced earlier in this section. It's approximately 2.71. And when you use base e, some magic happens, especially when you do calculus on natural log of x and so on. What happened is something just wonderful, so wonderful that I can't wait to tell you about, but I'm going to have to wait, all right? Now, why is this ln? It's called a natural logarithm. I think you can blame the French for spelling this ln as opposed to nl. Natural logarithm should be spelled nl, but over there in France, they use the adjective after the noun, so it becomes log natural, whatever. Ln is how they spell the natural logarithm. All right, so with these two, again, this is the most natural choice, and you will see why. I know I keep saying this to keep you in suspense because I want you to wonder why this E is such an important base in terms of mathematics and calculus, and you will see the answer hopefully by the end of the semester. Okay, so that's that. All right, now let's look at the properties of log very quickly, and then I'll let you do some review homework problems. All right, so you remember, let's say here, let's say let b of x be m, b of y be n. Okay, you know b of x, what should I say? B of x times b of y is e to the x times y, right? Okay, so we know this. Now, by the way, you can rewrite this as log base b of m is x, log base b of n is y. This one is saying, what is that? This one is saying, well, m n log b of mn is equal to x plus y. You see what it is? This is m. This is n, right? So the log of mn with base b is, of course, the exponent, which is x plus y. Okay. You know what this says? All this is saying is log b of mn turns out to be x plus y, because that's what happens with exponents, right? When you multiply these two numbers, then the exponents become additive or become the sum of the two exponents. But x happens to be this, and y happens to be log b of n. Okay, so this is why that strange property that you learned back in pre-calculus or whenever is true. Log of a product turns out to be not the product of the logarithms, but the sum of the two logs. This is very weird. In no other parts of mathematics do you see the product being transformed into addition. But that only happens because we are talking about logarithms, which have to do with exponents. Okay, so the log of, let's say this in English again, the log of a sum, the logarithm of a sum is the sum of the logarithms. Sorry, the logarithm of a product is the sum of the two logarithms. Okay, now using similar arguments, we could also prove that log of m divided by n, the log of a quotient is the log of m minus log of n. So the logarithm of a quotient is the difference of the two logarithms. And finally, this is maybe the best of all. If you raise this to the kth power, log of m to the kth power turns out to be k times the log base b of m. So in a sense, and I call this kicking, like if you think of this like a ball, on the top of somebody's head, and you can sort of kick it to the front, and it comes right to the front. It's sort of like picking up a soccer ball with your 2 feet and then kick it and put it right in front of your defender or something. So this thing that used to be behind m comes in front and becomes the coefficient. Okay, now this is incredible. I know this is, yeah, you have to memorize this. Yes, you probably do, but just appreciate this. Imagine how wonderful this is. What used to be an exponent, which is hard to handle, can now be made into an exponent. Okay, again, nowhere else in mathematics or in any other areas can you do this kind of thing. An exponent becoming a coefficient, because coefficients are much easier to handle, right? So these are some of the properties that you can use. All right, so let me practice or give you some practices. What is log 2? You know what this is? No, you don't. Okay, I don't know what that is either. This is 10 to what number is 2? Okay, I know the answer. Oh, yeah. 10 to the 0th is 1. 10 to the 1st is 10, right? And 2 comes between them. So I know the answer is somewhere between 0 and 1. Now, if you have a calculator, you can do log base 2 of, log base 10 of 2, and you can get the answer, okay? But that's not the point, okay? We don't know what that is without using the calculator. What is log 5? I don't know that either. It's also between 0 and 1. It's bigger than log 2, but it's, less than 1. But even though we don't know what log 2 is and what log 5 is, I know the sum of these. How do I know that? Because the sum of these two logs is the log of the product, which is log 10, and that's 1, right? 10 to the 1st power is 1. So even though I don't know this or that, I know the sum of these, which happens to be 1. Okay, what is the natural, if you are on a contestant on Jeopardy, and the final Jeopardy question says, this is the number, that's the answer. What's the question? What is this? Do you know what e to the 14th is? No, you don't. Okay, I mean, again, it's a very big number, and I don't know what that number is. I really have no idea. I think it's over 1 million, but maybe it's over 1 billion. It's a big number. No, it can be over 1 billion. All right, but what is the natural log of this? You know what that is? Well, you can kick this in front. So this is 14 times log of e. Now, of course, the natural log of e is the question, e to what power is e? Okay, well, e to the 1st is e. So that's 1, of course, and the answer is 14, okay? And again, you can tell this is 14 because e to the x and natural log of x are inverses of each other. And of course, if you do the exponentiation followed by its opposite or undoing of it, of course, you'll get the initial input value back, which is 14. All right, so you could do something like this. If, I doubt you're going to see this in Jeopardy, but if you're on a quiz show and if somebody asks you to find the natural log of e to the 14th, you can just say, oh, that's simple. It's just 14, right? Okay, so you have many interesting questions. And this brings us to the end of chapter 1, section 1.5, and that's the last section of chapter 1. So next time we'll see you, it'll be the beginning of chapter 2, and that is the introduction to calculus. So we look forward to that, and until then, I hope you have a wonderful day, and I will see you later.